Okay, so let's get going. It turns out, actually, today's lecture is not bad in terms of the amount of material. But the bad thing about this one is it's just the concept that you have to sort of wow. It is a new concept, I would say, because it's nothing related to things that you probably have done in high school or in physics one. So this is something that we're going to extend our understanding from previous stuff that we have done from electric field, electric potential come along toward the end because they are related. We saw that last week. However, what we are about to learn today is something that linked between the electric field line. Okay, we use that one to visualize the electric field around any electric charges. So we sort of know that we visualize that around any charge there will be like some sort of like a field coming out of it if it's a positive charge, and there's a field points towards it if it's a negative charge, right? But what we are trying to learn today is actually there is a connection between the density or the strength of that field, okay, the strength of that field, and the size of the charge. It kind of makes sense because if you have like a big charge, like like a huge amount of charge, the electric field that coming out of it will be very strong, right? And if you have like a tiny charge, then the electric field around it will be weak. So that means there is a relationship that's linked directly between the strength of the field and the amount of charge in it. Okay, sounds good. All right, so that's the key of what we are about to do today is the Gauss's law. That's what we're going to do. Okay, so we're going to talk about that electric field lines one more time, and we're gonna name those quantitatively. So that means it seems like we are able to count, but we are not gonna really count it. But it's like we will quantify that electric field lines, and you will see at the end that those amounts or the density of lines linked directly to the charge. Okay, all right, and that is the main goals of first half of today's lecture. Okay, but after sort of like understanding the Gauss's law, then there will see some you will see some applications, and the main applications that we're going to look at is the capacitor, which is the electric device that you use like pretty much everywhere. Okay, so we'll see the connections toward the end of today's lecture. All right, so that's enough for the introduction. This is what we're about to do. All right, stick with me. If you kind of like do not understand anything at like the first pass of this one, that's okay. All right, because that's mean you're going in the right direction. All right, like think positively. Okay, so this is the key. What I was saying that if you can count the number of the field lines, if you can count, of course you're not gonna really count it because this is just the visualization, right? This is your imaginary line. It's not real. But if you were able to count, okay, and then you divide it by the area that you are sort of like the location that you are counting, then you divide it by that. Then that will give you the density of those electric field lines. Yeah, that makes sense? So that's a figure on the right is showing. So you can guess if the line density is high, so that means the electric field in this area is going to be very strong. If the number of lines are very small, then the density is also small. So that will indicate that the electric field strength in this area is going to be weak. Okay, that's it. So it seems like you should be able to tell the magnitude of the electric field by looking at this ratio right here, which is just the line density. Okay, so what we are gonna talk, because we don't want to keep saying that the electric field lines, and we want to count the electric field lines, then that's gonna be sort of like mouthful when we want to talk about it. So we're gonna call these just the flux. Okay, those lines that coming out, that's sort of like pointing in space and everywhere, then you were just gonna call them, those are electric flux. Okay, so the number of those lines, you can call it electric flux. So we're gonna use the notation, the phi, which is very nice. Okay, it's flux for that. Okay, so in conclusion, you can move the area to the left. Okay, so and then we can actually turn this proportional equation into a real equation by just say the number of lines, which is we're gonna call them from now on electric flux, is just a product between the electric field multiplied by the area. Sounds good? Okay, cool. But if you notice, we have the perpendicular subscript symbol right here. Okay, so that means there must be a way that we should be able to count this properly. When I say count properly, what does it mean? Okay, look at this area one more time. If I'm asking you, hey guys, how many electric field lines that passing through this area? What I can just do is just okay, Dad, I'm just gonna count them. 1, 2, 3, 4, 5. Then there are 1, 2, 3, 4, 5, 6 rows. So there are 30. All right. Okay, once again, we are not really counting it in reality, but just for this figure right here. So for this figure, I can say there is the 5 across, 6 row, so there are 30 lines, correct? However, if I have another set of lines that actually penetrating in this direction. So that means what I'm saying is if these 30 lines of electric field do not point perpendicular to the area, would you count 30 as the number of lines that going through? What do you think? Right? I will go for like an extreme case. If those 30 lines, actually I should undo. Sorry. All right. So if all those 30 lines are pointing in this direction, okay, I'm just going to draw like maybe 4 of them. So I will ask you, hey guys, how many black electric field lines that going through this area? What would be your answer? What do you think? Oops. It's kind of hot in here. Okay. What do you think? So if those lines are actually point parallel to the area, not perpendicular, how many lines is actually going through this area? What do you think? So you say, well, Ajahn, this will give you 0 because it's not going through. It's not penetrating the area. You guys with me? Yeah. So to be fair, when you want to count the amount of electric flux, which means the number of lines, you should count only the electric field that going through the area properly. So now you understand what I'm saying properly means perpendicularly. Okay, so if you look sideways, so this is the edge of your area. So you just would like, you would like to count the electric field that actually going in this direction. So you count that 100%. 100% means you count them all. However, if you have this, the black line, this actually gives you 0 flux through the area. Okay? And here comes the question. Okay, Ajahn, what if I'm coming in an angle? How you would like to count this? Very good. I think what you're thinking is correct. All you need to do is doing the components of the vector. So now I can break this blue electric field lines into 2 components. See? With me, guys? And you can say right away, Ajahn, the vertical components, that's not good because this component is actually not penetrating the area. I'm going to take only the horizontal component and I'm just going to count this. So if you see, I'm only going to count the components of the electric fields that point perpendicular to the area. Looks good? All right, I think you guys just like, what we are doing here? Okay, stick with me. It's gonna be like I'm gonna take like a long time explaining this to you guys because you need to understand this. Once you understand this, the rest of the Gauss's law is, I would say, nothing at all. It's done. Okay, so the key is understanding electric flux. If you understand what the electric flux is, Gauss's law is just, just a snap. Very easy. Okay, kind of get that? Okay, so if you get this one, I'm just gonna stick with my drawing right here. What will be the easy way that you can count this systematic way, in a systematic way? You don't want to just like keep doing like, hey, let's break the electric field into two components and then try to, well, imagine what the area is. So the systematic way that we usually do, and actually we do this all the time, is this. Okay, look at this. So now if you have electric field point, in this case perpendicular in the vertical directions, and now your area is somehow making some angle to it. So it means there is another perspective to looking at this scenario. You might say, well, Ajahn, it turns out we're gonna focus on the electric field, and it turns out the area itself that is not perpendicular to the field. That is fine. Okay, you guys see what I'm saying here? Yeah. What we saw from last in my drawing is we stick with the area, and we are trying to look at the electric field that penetrate this area in the perpendicular direction. Or you can look at this in another perspective. Is that, well, Ajahn, actually electric field is already pointing there. The area itself is actually not in the perpendicular directions or the perpendicular orientation. So what are you going to do? Well, Ajahn, actually, can we do a component of the area? This is kind of weird. Right? It sounds really weird, right? Can we do a component of an area? All right, before we doing that component of the area, you're probably confused about Ajahn, area is not a vector. So when I say, okay, let's talk about the component, it's not going to be a component at this point, but it's going to be like a projection. Look at this one. So if you would like to count the amount of electric field that going through this area, actually what you need to count is just the electric field that going through its shadow. Can you see that? You guys with me? I try to draw this one in a black color. Yeah? So actually what you see on the right, this is the shadow casting on the actual area, the blue one, by imagine that the electric field direction is the direction of the light. Let's say like you shine the light in the downward direction, and you shine that onto the area on the left. Okay, this one. Okay, if you shine the light downward, hitting that tilted area A, then the shadow casted by this light is going to be the shadow on the floor, right? The black one that I just highlighting right now. With me? So actually, what you see on the right, that is, you can think of it, this is the shadow, okay? In the direction that it turns out, the shadow, you can see that is perpendicular to the E, because E is the light, right? You think of it as light. So you shine the light in the downward direction. The shadow on the floor is going to be perpendicular to that direction of light automatically. Yeah, that's nice. Okay. So this is another way to look at the scenario between the electric field lines and the area. No matter what you're trying to do, the key point is I want these two to be perpendicular. That is the key. Okay, the drawing is not so clear, but I want them to be perpendicular. Okay, we only going to count the flux when the electric fields and the area are perpendicular to each other. Got it? Okay, very good. Okay, you can sort of chat a little bit about how well we are doing right here. All right. Okay, if you get this idea, now I am trying to get you to this. expression. But I want to show you right now. How do you feel if I'm writing something like this? Does this sort of bring back any memory? The electric field, the area, and the cosine of the angle, something. I don't know. You sort of feel a little bit about, oh, this equation is sort of familiar. Yes, you got it from Fs cosine theta, right? At the time that you were doing the work done by the force. When you're doing the work calculation, you say, Ajahn, I would like to calculate the work done by the force. What I'm doing is I take the force, multiply by S cosine theta. S cosine theta is the displacement in the direction of force. In the direction of force. In the direction of force. So this one, if you draw this one or write this equation in the vector form, it's a dot product between the vector F and the vector displacement vector S. So the dot vector is the operation that bring the vector and multiply by the other vector that's pointing in the same direction. That is the operation of the dot products. The dot product is trying to multiply two vectors that pointing in the same direction. Okay, so if these two are not pointing in the same direction, what you do is you take the cosine theta. So there will be just only the component that is pointing in the same direction. Okay, sounds good? It's kind of like you have seen this before. So if I have this kind of idea back in the day of work calculation, I can sort of now interpret what we are trying to do right here is, oh, Ajahn, it seems like, it looks like what you are trying to do is you're trying to do the dot product between two vectors. Electric field vector seems okay because we define electric field as a vector. But the area, we have learned this to be just a scalar quantity. It's the width times the length, you get the area. So how can you now want A to be the area to be a vector? And now what I'm saying right now is, yes, I am bringing area to a vector form. And this is what we are about to do. Okay, look at this plane. Okay, the red plane over here. Okay, that's, yeah, I think it's just the back of my phone. Okay, so if you look at this surface, the red surface right here, okay, if I put it flat like this, versus if I put it vertically, of course, the area is going to be the same. Width times the length, the area is the same. However, the orientation are not. When I put it vertically and I put horizontally, the orientation are not the same. So this is the key. So the reason that I want the area to be a vector now, because we would like to incorporate the orientation of the surface into this area as well. So we are not just only care about what is the size of the area. We also would like to take care of the orientation of the area. Okay, and how are we going to do this easily? The technique is we're just going to put a vector that's points perpendicular to the actual area. You guys with me? Okay, look at blue pen over here. So if you look at this one, when I place vertically, yeah, so the vector will point horizontally. Yeah, okay, with me? If I place this horizontally, the actual surface is horizontal, then the vector will point actually perpendicular up like this. So by having this vector right here, so now I can actually say which direction of this surface is actually pointing to. I can do it actually in 3D. I can now point it in any directions I like, because I know if I see this vector, I can sort of trace back to the actual area that is going to be perpendicular to this vector all the time. You guys with me? Okay, one more time. If I see this to be an area vector, I will know right away that the actual area is going to be perpendicular to this. So that means I can point this towards you. I will know that the actual area is going to be perpendicular to this. If it's pointing up, I know that the actual area is going to be horizontal. If I see the area vector pointing horizontally to the left, well, to my left, then the actual area is going to point like this. Okay, sounds reasonable? So that means from now on, every time that I see a surface, I can draw a vector perpendicular to that surface, and that will be the area vector of that surface area. And you're probably now wondering, well, Ajahn, wait a second. Who tells you to create a vector that pointing in that direction? What about the back side of this? Why don't you pick that? Why you pick it this direction here? The reason is right now the surface that I'm holding here is an open surface. You guys with me now? It's open. It's open surface. So when the surface is open, then you have choices to make because there are two open surfaces, right? So you can choose to be left or you can choose to be right. Yeah, you're right. So if this is open, then the direction of the area vector is still sort of like you still have to make decision which direction you want to sort of pick. However, what we are going to learn in this lecture, you always talk about the closed surface. The closed surface. Okay, what does it mean by closed surface? So I will bring a box here. Okay, let me bring in a box. Okay, let me do a green box here. Okay, so if I have a box, this is a closed surface. You guys with me? It's closed. Okay, so when it's closed means there is an internal volume to this surface. And if I look at the top surface, I can now draw a vector perpendicular to it. And then I say, hey guys, the direction of the area vector will always point outward from the closed volume. Okay, you guys with me? Okay, come again. So if I have a closed surface, this box is closed. You can think of it like a balloon. Balloon is also a closed surface. You can think of your body, well, not totally close, but very close to very closed, very close to a closed surface. Okay, so if you have the surface that wrap up on itself, then you can enclose a volume inside this surface, right? So the vector will always point perpendicular to the area in an outward direction. An outward direction. So that means if you have this box right here, okay, so the top surface will have the area vector pointing up. The bottom surface will have an area pointing down. The front surface will have the area pointing towards you. The right surface will have the area point outward like this. Yeah, you guys sort of understand what I'm saying here. And the easiest maybe or the closest example that will indicate the direction of the area vector is your hairs in your body. So if you can imagine that if your hairs just sort of go straight up, like this, everywhere in your body, that is the direction of your area surface. Of your area vector. Okay, so if my hair is standing up, then that will be the area vector of my body surface. Okay, sounds reasonable? Okay, so come back here. Here. Okay, because right now it's open. Okay, so it's done. It's too bad, right? But now you get an idea that, okay, let's give you an example. I can actually draw this to be my area vector. Okay. Even though you can also point in the opposite direction if you like. That's the idea. But eventually, we're not going to have any confusions about which direction to pick because we are going to deal with the closed surface. But right now, for the open surface, I'm just want to talk about the concept of vectors from the area. So right here, think of it as just a regular vector. You can always break this into two components all the time. No big deal. Okay. So just to be clear, so I'll use a different, let me use the different color. Okay, give me 1 second here. Okay. So I can break this into two components. There you go. The green component and the black component. Okay. And now you can imagine that the black component, I'm going to call this a perp because this area is pointing up. Remember that every time you have an area vector, the actual area is going to always be pointing or oriented in the perpendicular directions relative to the vector. So when the A perp is pointing up, the actual area is going to be perpendicular to it. You guys with me? So that is the black area down there. Look at the green. If the green is your area vector, the actual area vector for that green vector is going to be perpendicular to it. I don't know if I can draw this properly. Here we go. There. Is it good one? I hope it's good. Okay, all right. Not too bad, I hope. Okay, you guys see what I'm trying to do here? So look at the sideway. So the blue area is point here, oriented in this direction. That's your area. Sideway may be easier. So the area vector is pointing perpendicular to it all the time. Okay, I'm breaking this area vector into two components, the vertical and the horizontal. Yes? All right, cross that out. Okay, so the black component, which is I'm gonna call A, it doesn't have to be A perpendicular, but this one component of this is going to represent the area down here. That's the black. And for the green, another component there, that's going to represent this area right here. With me? Okay, so now it seems like the area itself can be thought as a vector due to their orientation. And once the area turns into a vector, you can break a vector into two components. So the components of the vector represent the projection. When I say projection means, look at the black. It's just like I have like a flashlight and shine the light downward, okay? And that light, once it hits the actual area, the blue area, then it will cast a shadow down here. That's why we call it the projection, because the black area is just the projection of the actual blue area. Look at the green, same thing. It's the same as I have a flashlight, try to shine the light horizontally. Once this light hit the blue area, it will cast the green shadow on the screen. So that is the projection of the blue area, okay, in the direction of the A vector. I mean the green vector, sorry, the green A vector. The components of that. What do you think? Does it sound all right? This is the hardest part of today's lecture, I guess. It seems to be the hardest thing to imagine, because this is the well, the concepts of area vector. Okay, guys, seems okay. Just maybe type 1 if you're okay. And just type 0 if you're like, what is going on here? Oh, okay. It's still, oh, 0. Oh, oh my God. All right, not good. 0 is not good. 0.5, okay, like so, still confusing. Okay. All right. Oh, some of you get 1. All right, not too bad. Okay, so, okay, keep going. It's still, I mean, we still have something else to show you. Okay, that's just to get you going in this idea. Okay, just get the idea of projection, the idea of having a vector to be a, having an area to be a vector now. Okay, now, here, this is what we are trying to do. Here, look at this. So, now we kind of get it. that every time you see a surface, okay, you can calculate the area of that surface. You can now draw a vector perpendicular to that surface that will represent that surface in the vector fashion, okay? All right, so that's sort of like the overview of what we are doing. So look on the right. Okay, so let me redo the whole thing that we have been doing one more time. So look now, the green surface having the area A. Okay, all right. Now, the electric field point per horizontally, that's no big deal. But then what we are about to do is we would like to define a vector of this area. Okay, so that means what I'm doing is I have to draw the vector that point perpendicular to it. That is the green vector in figure C. Okay, that is your area vector. Yes. Okay with me, guys? Okay, good. Now, once you define this area vector, now you start seeing that now there is an angle that this vector A is making with the vector electric field E. Yes? You guys with me? Okay. So, the figure B, that was the first case that we did when we introduced the electric flux. What I can do, first choice, is breaking the E into two components. I can break the E into a vertical component and the horizontal component, right? Okay, you guys with me? Yep. And then I said this parallel components of the E does not contribute to any electric flux through this area, because electric flux only count towards the electric fields that point perpendicular to the actual area. So this is the only component I'm gonna count towards the electric flux. Okay, you guys with me? That's figure B. Or in the other way, what I can do is I'm just gonna stick with the electric field that's already point in the horizontal direction, and then I'm gonna break the area vector instead. So that means what I can do is now I can break A into two components. With me? Okay. The only components that I'm going to take into consideration is just the horizontal, the electric field. The area vector that actually point horizontally. Why? Because this is going to be the vector that is representing the actual component of the surface that is perpendicular to the E. Is the shadow. So figure B and figure C will end up with the same amount of the electric flux. But the figure B, you are breaking the electric field components and you only consider the components of the electric field that is perpendicular to the surface. In figure C, you keep the electric field fixed, and then you only consider the component of the area vector that actually representing the surface that is perpendicular to the E. But no matter which direction you're going to take, you're going to end up with the same results. The reason is because what we are doing over here is we want only the vector, here we go, electric field vector and area vector that is pointing in the same direction. Yes? Make sense? We only gonna grab the electric field vector and the A vector, and we're gonna combine them, only taking the components that are pointing in the same direction. Okay, right here, you see that? is either E and the A in the same direction as E, or if I draw overlay the A vector up here, see, is the component of the E that pointing in the same direction as A, or is this component of A that point in the same direction as E? Whenever we have two vectors and we want to take the product between these two vectors, but only grab the component that are pointing in the same direction and combine or multiply, then we do the dot product. Yes. So it's pretty much the same thing as the F dot S, right? Because when you do the F dot S, you can think in two ways. You can break the force components and you only take the component point in the same direction as the displacement vector. Okay, let me give you an idea here. F, S, right? So what you can do is you break F into two components and then you take only this component and multiply by this. Or on the other way, you can do S cosine. This is F cosine. There you go. I don't know is this help or not, but what, oh shoot, I shouldn't do it all in one. Okay, one more time. Here we go. All right, so this is what you did before. Okay, let me try again. F cosine. Why is it red? Okay, here we go. There you go. Okay, so when you have the force, okay, that is not pointing in the same direction as S, you take the F cosine because that is the component that is pointing in the same direction as S. But the other way that you can do, same scenario, what you can also do is you take the S cosine theta and multiply by the F. Same thing, you end up with the same. W equal to F cosine theta S, or is it F S cosine theta? Whew. I don't know. I'm explaining good enough or not, but that's what it's about. What this is about is we are trying to multiply two vectors, but we are going to take only the vector that point in the same directions. Every time that we want this kind of product, we do the dot products. But one thing that we sort of incorporate into this is whenever you see the area vector, the actual area is actually perpendicular to the vector. So that means the surface itself is going to orient or has the orientation of that perpendicular to the area vector A. So that means every time that you have the electric field vector, okay, parallel to the area vector, that means the electric field vector points perpendicular to the surface already, because we define the area vector to be perpendicular to the actual surface. So whenever E and A are parallel, it translates to E is perpendicular to the actual surface already. And that's our definition of the flux. We only count the electric field that points perpendicular to the surface. Woo. Better? I don't know. All right. So if this is still, well, still kind of vague, so we're going to have exercises, okay? And we are going through exercises to help understanding these concepts. Okay. All right. You can always type 0, 1.5 all the time when listening to me. So at least I get some feedback that how well is going. Okay. So before we look at exercises, because now I turn this flux into just the dot product between the electric field vector and the area vector. Okay, now, of course, you can write it out as a E times A times the cosine of the angle between two vectors. And now that's come back to this slice right here, EA cosine theta, right? So because it's the cosine theta, so that means the angle between E and A vectors can be less than 90, greater than 90, or exactly at 90 degrees. So that's why it turns out the flux, okay, can be positive, 0, or negative. That's okay. Okay. However, what does it really mean when you have positive flux? And what does it really mean when you have a negative flux? Zero flux is easy because it means there's nothing going through the surface, right? So look at this one. Now this is now exactly what I'm talking about. This is a closed surface. It's a balloon, closed. So there's no doubt now that every time that I'm looking at a surface, a tiny portion of the surface, I can always draw a surface vector or area vector. That's my A. Let me call A1 right here. Okay, with me, guys? Okay, so now I can just, oh, Adan, here. That's my A. Here we go. 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 Yeah, that's what I'm talking about. That is the area vector. Okay. Now you can say, oh, Adan, I can keep drawing area vector. Area vector. It's kind of fun, yeah? Everywhere. You can do it everywhere you like. Okay, area vector, area vector, area vector, something like that. Okay, so just draw the area vector perpendicular to the surface all the time. And now it's pointing outward from the enclosed volume inside. So now there are no more ambiguities or anything because there's no inner, there's always inward and outward when you have a closed surface. And our area vectors are pointing outward all the time. Outward. Okay, good. Now, if you look on this side over here, you can see that the angle theta is less than 90 degrees. So that means if you look toward the right side of this balloon, the flux going through the surface on the right side of the balloon seems to be a positive flux. If you look down here at the surface number 2, it's accidentally at 90 degrees, which is fine. So over here at the surface number 2, flux is 0. Okay, flux is positive. On the right, flux is 0 on the surface number 2, which is okay. It means that there is no electric field vector penetrating the surface number 2. That's okay. Number 3, it turns out if you look here, it's like, oh, John, the angle, okay, if I draw this line, extend it out a little bit, now the angle is greater than 90 degrees. So the cosine of the angle greater than 90 degrees give you negative value. So that means over here you get a negative flux. Flux is less than 0. Okay, cool. So the reason that I want you to look at this sort of complete picture here because now you know what the flux means. Flux is trying to tell you how much or how many electric field lines is actually piercing or penetrating outward and how many is trying to penetrating inward into the balloon. You guys with me? So that means if I can count all of this amount of flux through this tiny surface, so I mean just count all this flux. So that's why in the textbook they put like a delta flux here. When a delta means it's just a flux through that tiny surface. And then if you just keep counting, keep doing this on all those tiny surfaces, just keep doing. And then you sum all those flux. Right? So you sum them all around this balloon. you will get a net flux. Net. Oops, sorry, net. So what does the net flux is telling you? It's telling you that within this closed surface, at the end, is there any electric field going outward, inward, or nothing at all? Yes? Okay, let's think of it in the other sort of scenario. If this figure over here does not represent an electric field, let's say if this figure is representing a stream of water, so that's orange lines there is giving you like the sense of there is a water flow. Okay, think of it that way. And the balloon is you like maybe like a tank that you want to sort of keep some water to yourself or something like that. So you see that there is a water flow from left to right. The outward flux is trying to say how much water is actually flowing out from your volume in your balloon. On the left, it's trying to say how much water is actually flowing into your volume inside your balloon. If you eventually find the net flux, you should be able to tell in your balloon eventually you're going to get more water because in is more than out, or the water in your balloon is actually going to get smaller because out is greater than in, or the amount of water in your balloon is going to stay the same because out is just equal to the in. So you can think of this like a water flux if you want. It's like a stream of water. Okay, so you can think of it as like the flux is a general idea of something that's actually flowing, and you want to quantify that. That is fine too. Or another scenario, you can think of this orange line is representing the heat transfer. There is some energy flow from hot to cold, for example. So this is the amount of heat the energy is actually flow. And then maybe your balloon is your room, for example. And you want to calculate the heat flux. So the one on the right is telling you that there is the energy is actually flowing out from your room. The one on the left is trying to say, hey, there is the heat flowing into the room. If you figure out the net flux, so you should be able to see that your room is going to get hotter or cooler, depends on the amount of heat flow. You guys with me? If out is greater than in, then your room will be cooler. If in is greater than out, then the energy is higher, so the room should be hotter. Or the room in your balloon stays the same if in and out are equal. And then what we are doing here is electric flux. So what are you trying to say is, hey, within this volume, how many electric field lines is actually penetrating outward? And how many electric field lines try to get into this? Okay? If the net is positive, it just means, oh, within your closed surface over here, the net electric field is outward. If in is greater than out, oh, this closed surface have net of inward electric field. Or if the out equal to in, you will say, oh, there's nothing here. There's no net electric field going on. I mean, net flux, sorry. Net electric flux is 0. So nothing in there. In equal to out. Woo! Sounds good? Okay. Is that getting better a little bit? Maybe? Okay. So let's look at some exercises. Okay, point 6. Okay, a little bit of improvement here. All right, here we go. So what we are doing over here is we would like to calculate, okay? When you have a closed surface, you would like to calculate the net flux. Okay, yeah, that's what we are that's what we will do in this lecture. We will try to calculate the net flux through a surface, but that surface is not any surface. It's always a closed surface all the time. Okay, so we're gonna draw this one like a calculus, a little bit sort of ish, but it's not that bad. So what we're trying to do is, of course, let's start from, you can always slice this, okay, closed surface into a tiny, tiny piece. So you can name this surface to be like a dA if it's really, really small. If it's not very small, you can call it delta A. But once that piece is going to zero, super, super small, you can call it the differential of A. But no matter what you have, you're going to always have a vector associated with this all the time, right? And we know we just draw a vector perpendicular to the surface. So that will be your dA vector. Okay, now if you know the angle that dA vector make with the electric field vector, the flux through this surface right here, just only this piece of surface, will have flux equal to E dot dA. You guys with me? Yeah, simple. However, because this flux is going to be pretty small as well, because the area is super, super small, let me call this differential of flux, a tiny flux. And if you want to know, hey, John, I want the net flux, what do? You do this everywhere on the surface of this balloon. Just keep doing, 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 keep doing. So on each tiny surface, you do E dot dA, E dot dA, E dot dA, E dot dA. So you get E dot dA, 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 and then you sum them up. But when you sum everything that is so small like that, it's just an integral. Once you complete the whole closed surface, that is your net flux through this closed surface. But just to emphasize that, hey guys, you have to do it on a closed surface. So they just want to put that symbol, a circle sign in there, just to make sure that, hey, don't forget to do this for a closed surface. It's just an integral, but it's an integral on closed surface. Woo! And that's it, guys. That is how you calculate electric flux from a closed surface. And what does it mean? It means you want to know how many electric field lines is going through that closed surface. If the net is positive, it means within that closed surface, there are electric field lines that coming out of it. If the net is negative, mean within that closed surface, there will be a net electric field going towards into that closed surface. If you do the net flux to be zero, it means there are no net electric field lines going through that surface. Okay, it doesn't mean there's no electric field lines. There are electric field lines, but the net is zero, in equal to out. Okay, whew. All right, let's give it a shot. And this is going to be, well, starting points. Okay, so let's go slowly. Make sure that you kind of understand this. If you do not understand this, just let me know. I'll just keep repeating until you understand this. Okay. So consider a uniform electric field E oriented in the X direction. Okay, very good. That's the orange electric field lines there. Find the net electric flux through the surface of a cube. So this is going to be our sort of starting point of a quantitative examples here. And the cube oriented as shown in the figure. So there's a cube of length L, placing there electric field pointing in the X direction. They want to find the net flux through this cube. Go ahead, guys. So I'll show you how it's done here first. Okay. First of all, there are 6 sides of the cube. Okay, so there's a bottom, the top, the front, the back, the left, and the right. Okay, you guys with me? Let's go an easy surface first. Let's try the top surface. What do you think about the top surface? If we call this surface number 3, the area vector of this surface will point upward. You guys with me? Perpendicular to the surface and pointing outward from the enclosed volume. Very good. Okay, very good. But can you tell what is the net flux on this surface number 3? Very good. It's going to be 0. Why? You can think naturally because electric field lines do not penetrating this surface at all. No, there's no penetration of the electric field line through this surface. It's just parallel. So it just sort of slide through. It's not going through. Or if you think in terms of the angle, the electric field vector is making a 90-degree angle with the area vector. So cosine 90 is 0. So actually this give you, let me say flux on the surface number 3 is 0. You guys with me now? Okay, try again. If you look at the front, would there be any flux through the front surface, you think? You say, well, Ajahn, electric field lines is also not penetrating the front surface. If I want to draw the vector for the front surface, I will have to go in this direction right here, right? So if you think in terms of the vector making some angle, that angle is also 90 degree again. This is not so clean. 90 degree. Still not very clean. 90 degree. Here we go. So once again, the flux through the front surface is also 0. And now you start seeing things here, seeing things. So you start seeing the trend here. The bottom surface will have the area vector pointing downward. But that will also make a 90-degree angle with the electric field lines. So no flux through the bottom surface as well. And now you will agree with me right away that also the same for the back surface. Okay? So the only surface that's going to give non-zero flux is going to be the surface on the right here, that I highlighting red right now. Okay? And it's going to be another surface on the left right there. I'm highlighting orange over there. Okay, you guys with me? Okay, so let's look at the surface number 1, which is toward the back. Okay, so now I can just erase them all. I hope you see what I'm trying to get to now. So just make it a little bit cleaner here. Okay, so what you see over here is now that the electric field is pointing along the x-axis, but the left surface having a vector point backward like so. Okay, so the dA of the area surface, of the surface number 1, making a 180-degree angle with the E. You guys with me? Okay, so let me draw on the side over here. So what we are looking at right here is the left surface. The area vector of the A is pointing to the left, and the electric field vector is pointing to your right. Okay, so this is a side view on the upper left figure over here. So that means the flux through the surface number 1 is going to be vector E times the vector A1. Let me call A1. That's your surface number 1 right here. And it's going to give you E A1 cosine 180 degree. Okay. And because A1 is just the area of that surface, it's going to be the length times the width. So it's going to be E L squared. Cosine 180 is -1. So it's a negative E L squared. That is the flux going through the surface number 1 on the left. Okay, let's do it one more time on the right. So that's my red surface here. Okay, so now the area vector is going to point perpendicular to this actual surface here. So let me call this A2. Okay, now flux going through the surface number 2 is going to be E dot with the A sub 2 vector. Okay, and that is E times A sub 2 cosine what? It's going to be 0 because now they are pointing in the same direction. And that will be E times A, which is L squared, times 1. So it's E L squared. I can emphasize it's positive. Okay, very good. So what is the net electric flux? So I would say, okay, let me call it net. It's going to be flux through surface number 1, surface number 2, surface number 3, surface number 4, surface number front, it wasn't on that, and flux through this back surface there. There are 6 surfaces, but the front, the back, number 3 and number 4 give you 0 flux. Nothing, 0, 0, 0, 0. So the net flux is just going to be negative EL squared from surface number 1 and plus EL squared from surface number 2. And that gives you 0 flux. And can you tell why it's 0? Well, Ajahn, that's not sort of unexpected because electric field is uniform. It's coming along, okay, x-axis. However, it's get inside this box. It's get inside this box through the left surface A sub 1. But then it actually goes out through the surface A sub 2. And because the electric field is uniform, in is just equal to out. So that's why there's no net flux left here. So the net flux within this box is 0. Start to see some sort of, something here. How to calculate flux. Whew. Okay, if this is good, it's getting better. It's getting better, maybe. Okay, all right. Let's move on to the next exercise. Okay, try again. Okay, it will get better, I hope. All right, I have quite several exercises to try. Okay, what is I L? Okay, L. Oh, the length is the length here. The length of the cube. So the surface, don't forget the area vector here, A2. Okay, it must have the magnitude and direction, right? The area must have the magnitude and direction. The magnitude is just the area. So actually it's L squared. Okay, so let me highlight this one. So the whole surface over here has the size of the area to be L squared. If you want to add magnitude direction to it, I can say it's pointing in around the x direction. I can say it's like L squared I hat if I want to. So if I want to talk about the magnitude of the area itself is just going to be L squared. Okay, would that sounds reasonable? Okay, very good. Okay, let's try again. Okay, if you are still sort of like confused a bit, the next one will confuse you more. But after this, I hope it will be a little bit clearer. Consider a closed triangular box resting within the horizontal electric fields. All right, you still have electric field in the horizontal directions. Okay, calculate the electric flux through, now you have to calculate the flux through the vertical rectangular surface. Okay, let's start with the part A. So let me highlight that surface here. So it's going to be this surface right here. That's your vertical surface. All right, so you guys help me calculate the electric flux through this vertical rectangular surface. Okay, let me draw sideways. I mean, this one on the side along with it, just to make it a little bit clearer. Okay, so when you look on the side, this is the vertical surface that we are talking about. I'm using the green color for it. Because the surface has to point perpendicular to the actual area, so let me call this A sub V. That's for vertical. Yeah, let's use that. And it's going to have to point to your left in this case, because it has to point outward from the enclosed volume. However, electric field is pointing horizontally. That's your E. So right now it's clear. Okay, let me write it on the side here. That's your area vector for the vertical surface. The magnitude of this is going to be the height times the width. So it's going to be 0.1 times 0.3 meters squared. You guys with me? Okay, the magnitude of this area vector is just the size of the rectangle. But the direction is pointing to your left. And now you want the flux through this surface. What you have to calculate is, okay, let me call flux subscript V is going to be E dot A sub V vector. Right? That's how you calculate your electric flux through a surface. However, you can see from the side view that A sub V vector is making 180 degree with the electric field vector. So it's going to be E times A sub V cosine 180 degree. And that is going to be a negative flux. We know that. Because electric field is trying to get in. Right? Electric field lines is trying to get in. Okay, very good. And that would be negative. Okay, let me just leave it there. E, okay, times 0.1 times 0.3. That's it. Just leave it there. You can substitute E whenever you like. And that's it for part A. That is the net flux through the vertical surface. Now, part B. Now they want the flux through the slanted surface. So let me highlight red over here. That surface right there. So if you look edge on side view, that is your surface here. That's red. With me, guys? Okay, very good. So if I want to draw an area vector, that will be it. Let me call this A sub S. Okay, or if I want to overlay on this, it's going to look something like that. A sub S. There you go. Oh, it's not. I think that's good enough. Okay. All right. Okay, nice. So with that, let me draw nicely here. Here we go. Yeah. Okay, so the electric flux through that slanted surface, let me use subscript S for that, is going to be vector E dot with the dot with the vector A sub S. Okay, very good. And that will be equal to E A sub S. Now, you probably can tell. Okay, John, let's call this to be your theta. That is the angle between the vector E and the vector A sub S. Okay, so you just have to put your cosine theta right here. Okay, very nice. This is the one I want you to focus on. This is it. If you understand how to do this one, I think you understand the rest of this. Okay, can you calculate this flux sub S for me? Seriously, like, do it. Can you calculate this one out? If you can get this one out, then this is going to be very good. Okay, if you're going to do through like a proper, traditional, straightforward approach, you can see that Ajahn, A sub S magnitude is going to be the width times the length. Okay, let me highlight black here, and there. The length is fine. The length is still 30 centimeter. But you need to calculate this hypotenuse here, right? Right there. So let me call it for now, this hypotenuse to be like B, length B. Okay, so that means the magnitude of the A sub S vector is going to be B times 0.3 meters squared. So this is straightforward. That's fine. Okay. And actually you will be able to calculate the B because you know the angle is 60 degrees. So you can use trigonometry to calculate the B. That's no big deal. However, if you look carefully, because this one is 60, okay, this bottom angle will be 30. If this is 30, this is going to be 30. And that means your theta is also 60 degrees. Correct? So actually you know the angle between the E and the A already. So what I'm going to do next is just say, okay, tan E times A sub S times cosine 60. However, you just say A sub S is just B times 0.3. Okay. So far so good. The question is, what is B? What is the length B? But then we can do trigonometry. You can use the 60 degree. You can say that the cosine 60 is the adjacent over hypotenuse. So adjacent is 10 centimeter, 0.1. Over hypotenuse is B. You guys with me, yeah? Yeah. Look at the right triangle over here. You have a 60 degree right here. So the 10 centimeter, that is your adjacent. The B, that's your hypotenuse. So the ratio between 0.1 and B, that gives you cosine of the 60. So the B itself is just 0.1 over cosine 60. I can plug it in here. So it's going to be E times 0.1 over cosine 60 times 0.3 times cosine 60 again. And you can see that cosine 60 cancel. You end up with 0.1, 0.3. Isn't that nice? Is that as expected, you guys? I actually don't need to do this trigonometry at all. The reason for this is because look at the electric field. It's point to the right. The slanted surface is not making 90 degree with this. I mean the surface itself. So you only need just the component that is perpendicular to the E, right? And we already talked about these concepts of the projection. So think of it this way. If I have a flashlight, like I said, and I've just shined a light against the E, what will be the shadow of the slanted surface on the screen that is perpendicular to the flashlight or the light direction? You get the black shadow on the left. Or what I'm saying is the shadow of the slanted surface, the red surface, will give you this shadow right here. With me? So that's why this 0.1 times 0.3, that is the AS perpendicular. It's a shadow. Yes? So actually, you can tell right away. Well, Ajahn, I'm just going to use just the vertical area because that vertical area is just the projection of the slanted surface.
Ajahn, why is AS shadow again?
YAS is what?
Shadow?
Oh, okay. One more time. So think of it this way. The red is the slanted surface, right? Okay. The electric field is pointing horizontally. So whenever we would like to calculate the flux, we only need the surface that is perpendicular to the E. Right now, the A sub S is not perpendicular. We only want just the components of this surface that is perpendicular to the E. So we do the projection. When I say projection means you can imagine like you have a flashlight, you shine the light in the direction of the E, okay, and then you imagine that you have a screen that is perpendicular to your light. Then the shadow of the A sub S, the red surface over here, will cast a shadow that looks like a black on your screen. Yes, yes, yes. And that black is the only component that is perpendicular to the E. And this is the only component that you need in your calculation. So when you look up top, yeah, that black shaded area here, that is the shadow of the slanted surface. When you shine the light, shine the light. Well, I was just trying to give you some sort of like real world situation that you can actually cast the shadow on it. But mathematically, we call it a projection of that slanted surface onto the surface that actually perpendicular to, I mean, on the wall, let's say, on the surface that perpendicular to the E. I don't know, does that help?
I understand now, have.
A little bit now. Okay, all right. We'll have a couple more to try. Okay, but let's finish this one. So I think we're done for part B. Now part C. Part C will be fine now because can you guys tell right away what happened on the entire surface of the box? What do you think? If you want the entire surface, yeah, very good. Very nice. 0 because there will be, even though you have a couple more surfaces to think about, but it contribute nothing to the flux because the front surface, no penetration. What about the back surface? Nothing. What about the bottom surface? Nothing. So that means the only two surfaces having the electric fields going through is either the vertical or the slanted surface. Okay, so that these are the two that eventually gonna have to take into your consideration. However, the in is now equal to out. Right? On the vertical is a negative, on the slanted one is positive, but the same amount. So very good. The net flux is 0. But you can actually look at this figure and you can see right away it has to be 0. Why? Because Ajan, in is equal to out. Right? I mean, you can count 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9. I mean, there's not actually 9, but I mean, from the figure, these 9 arrows coming in from the vertical surface, but eventually these 9 arrows going out. So there's no leftover inside the volume. So the net flux is 0. Cool. I don't know if it's cool or not, but that's how you calculate flux. All right, try again. All right, this will once again sort of pin down your understanding. If you can answer these questions, it means you sort of understand how to calculate flux, and you understand what does it mean by E dot A. A cone with the base radius R, the height is given H, located on a horizontal table. That is once again a uniform electric field horizontally in the horizontal directions. Determine the electric flux that enter the left hand side of the cone. Now they just want the left half. Okay, let me split this one. Okay, they just want the left half of this one. They don't want the right half. What is the amount of flux that actually go through the left half of this cone? All right, I'll give you a minute or two to think about it. Okay, first of all, if you try to think in terms of the area vector, on and on, wherever it is, it's gonna be quite tough because you're gonna have to figure out the angle between the E and all those area vector everywhere on the surface of the cone, which is gonna be crazy. And I don't think I'm gonna put that kind of examples here. However, with the concept of the projection, guys, ping, 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 light bulb popping up. So that means if I'm thinking again, take the E to be the direction of the light. I shine the light in the direction of the E, okay, onto the surface that I'm interested in. It will cast a shadow onto a screen that's perpendicular to the lighting. And the shadow that I'm gonna get is gonna look like this shape right here. You guys with me? Okay, let me draw it outside right here. You guys with me? Okay, so if I have a screen on the back and I have a cone in the front, I shine the light through the cone, it will cast the triangular shadow on the screen. And that triangle of shadow, that is just the components of the surface of the cone that is perpendicular to the electric field E. Because I know the base of this one will be 2r, the height is h. However, because you are talking about the left side of the cone, So actually what I am thinking about is going to be the area vector that's point to the left. Let me put subscript L for that. Okay. All right, very good. So that means you only take the left side of the cone. You do the projection. You only care about what is pointing to your left. So I can say the flux going through the left side of the cone is going to be E dot A on the left. But what I want is only the perpendicular direction to it. So it's going to be E A on the left perpendicular. And this is what the perpendicular means. Just the shadow. Just the shadow. So it's going to be E times 1/2 the base, the height. And that's it. E, oops, sorry. However, because the A vector right now that we are talking about is pointing to your left, so it's going to be cosine 180. A, the electric field is pointing to your right. A sub L perp pointing to your left. So there is a 180-degree angle between these two. So that means it's going to be a negative flux. We know that because electric field is trying to get inside this enclosed surface, this closed surface. So the answer is negative E R H. Done. Yes พอได้ไหม And actually, with this idea, you can calculate the net flux on the right side of the cone too. It will be the same amount, but it's positive. And you can still answer what should be the net flux through this cone. It's still 0. So I can say net is still 0 because entering and outgoing of the electric field lines are the same. The same amount enter and the same amount exits the cone. So that is no net flux inside the cone. Yes, better, hope. All right, so one last example in terms of projection here is, okay, because now I'm in my house, right? Okay, so the example that I love to do all the time is, so imagine that if you have a flash, okay, I don't know, will you see my, okay, here, oh, there you go. All right, this is good. All right, so if you think of this flashlight to be, the light that coming out of this one is like an electric field lines. And if I want to know, hey guys, what is the electric field going through my face right now? Going through my face. So what you really need to do is not trying to draw surface area vector of my face surface, my facial surface. You only care about what is the shadow of my face. So that means behind me, well, usually there will be like a screen behind me in classroom. But you see what I'm saying here? If I don't have to worry about the shape of my face. Only thing that I need to worry about is just the shadow of my face. And all I need to do is just take the electric field, multiply by the area of my shadow. So my face can look whatever, how weird the curvature, everything, it doesn't matter because it will cast the same shadow. As long as the surface area of this shadow stays the same, the amount of the electric flux through my face stays the same. This is not good. This one not good. All right. So my point is, what is sort of important here is just you care only the vertical component of the surface. Okay, because you want to count the electric field lines properly. when I say properly means just only the electric fields that going through surface perpendicularly. That's what it is. Okay. All right. If that is good, then actually this example you can, I kind of like, I don't want to take it as a DIY, but if you want to try, it would be nice. But I think maybe it's a little bit too much already, because this exercise try to bring you back to the IJK notation, and some of you not very comfortable with this kind of like vector notation yet. So that's okay. I think this one you can skip. It doesn't really hurt anything. Okay. And it just maybe confuse you even further. Okay, so let's skip this one. All right. So now before the break, this is the highlights. The reason I say it's highlight, and I said, if you understand how to calculate the, you guys hearing this sort of construction noise a little bit? Sorry. I think maybe that's somewhere next door. Okay, so when I say, why do we have to calculate this electric flux? And the highlights is this. Flux calculation is trying to tell you, are there any net electric field lines through the closed surface, right? If it's positive, something is coming out. If it's negative, something is trying to, not something is an electric field, sorry, not something. If it's positive, mean electric field is try to coming out from the closed surface. If it's negative, mean the net electric field is trying to get into the closed surface. If it's zero, means in equal to out. Who's responsible for this? Who is responsible for generating the electric field? Of course, the charge. Because we know positive charge generate electric field outward. Negative charge generate electric field inward. So if you know what is the net electric field lines through any closed surface, that has to link directly to the charge in that closed surface. Get me? And that's it. This is what we have been doing, trying to calculate the electric flux. But the guy who's responsible for this is the charge. So I put the subscript INC, that's just for include inside your closed surface. You only have to worry about what's inside. Okay, what's outside, I don't care. Because what we are trying to do is we want to calculate the flux that actually going through that closed surface. The epsilon naught, that's too bad because we just have to make the units coincide between left side and the right side. So that's okay. But at least the key concept is the flux linked directly through to the charge Q. Okay, sounds good. So look at this one, guys. If I have a charge Q here and I wrap this charge with surface number 1, surface number 2, surface number 3, what would be the net flux through the S1, S2, S3? They are all the same. And it's going to be equal to Q over epsilon naught. Believe it or not. So that means if you understand how to calculate the flux, all you need to do is just count the amount of charge inside your closed surface. It has to link through the Q over epsilon naught all the time. Look on the right. If you come up with weird surface and inside your closed surface does not have any charge in there, so I can say right away the net flux in here is going to be 0. Because there's nothing inside to have your net electric field through your closed surface. Yeah? Yeah? Reasonable? Okay? So that's what it is. That is Gauss's law. Believe it or not. And that's how easy it is. But before the break, I will just leave you with this simple, very simple, uh, well, it's just a qualitative exercise. A cross sections, all right, the two Gaussian spheres and two Gaussian cubes. All right, don't worry about this Gaussian. We'll come back to that. But the idea is, if you have a charged cube at the center of some surfaces, over here you have like a sphere wrap around it, a cube wrap around it, various sizes. I don't know what it is. Which one will give you the largest amount of flux through? You will answer that all the same. And the flux through this one is also exactly Q over epsilon naught. You're done. Simple. Okay? I would say simple, but at the same is the hard work has already been done. The hard work is on the left. Because this, you have to come up with E dot A, do the integration sometimes, or do the summation sometimes. But once you're done with that, all you can relate back is just, hey, the guys responsible for this electric field in and out is just going to be the charge that is inside your closed surface. So this is a reason why, if you come back here, all three exercises that we did, now you understand why your net result is 0. Because there's no charge in the box. That's why you're gonna get 0 net flux. Here, second exercise here, why you get 0 at the end? Because there's no net charge in this triangular box here. This, why the net flux is 0? Once again, there is no net charge in this cone. Okay? Nice. And that is Gauss's law, guys. Cool. All right, let's take a break first, okay? And then we'll come back and we'll do some application of Gauss's law. But I think the hard work has been done. The rest is just applications.